Okay, welcome to lecture. We'll get started here in just a second. Continuing on with chapter 21. It's letting everybody in, hopefully. So again, we're on chapter 21, which is nuclear chemistry. We started it last time, and I think we left off right around here. And like usual, if you do have any questions, feel free to ask them there in the chat box, and we'll get that question answered for you. All right, so we started talking about nuclear chemistry last time, and a couple of things that we talked about. We talked about some different types of particles. Remember, there's alpha particles, which again is the helium nucleus. Can use the alpha symbol or the helium symbol basically to represent it. There's also the beta particles, which is kind of like an electron. So again, you can use the beta symbol or an E for kind of like an electron as the symbol is commonly used. We also have gamma, which is just pure radiation. So you use just the gamma symbol. There's things like positrons, which are also use the same sort of symbols as beta particles, but they are positive. So a beta particle would have a minus charge, if you will. A positron particle would have a positive one. Again, even though they use sort of the same symbols, the charge there is sort of different. So again, a beta particle would have the 0 minus 1, while a positron 0 and plus 1 would be the symbol that's there. Again, we have our alpha particles, which is our 4 and our 2. We have our beta, our gamma, which is 0 and 0. We also saw some other things like a proton is sometimes used, so either H or a P for a proton, also a neutron as well. So as we saw these particles, their mass number, atomic number is really important to know. Again, it's important because it will allow you to balance nuclear equations, which is sort of where we left off on. Balancing nuclear equations, again, it's a little bit different than chemical equations. And because, as we talked about, and as it sort of says here on this slide as well, in a nuclear equation, there's no conservation of elements. So what that means is what you start with in terms of elements, you actually make new elements at the end of it. And the way that we go about balancing them then is we use mass number and atomic number. So to balance a nuclear equation, what you're looking for is the same mass number. When you add up all the mass numbers on the reactive side of the arrow, needs to equal all the mass numbers on the product side of the arrow. And when you add up all the atomic numbers on the left-hand side of the arrow, it does need to equal all the atomic numbers on the right-hand side of the arrow. And if you remember, as we talked about, really your periodic table is sort of your best friend here when you're doing this. And that's because on the periodic table, the atomic number is what you can find. And a reminder, right, the atomic number is the number of protons that you find in an atom. And every element has its own unique atomic number, which means you can use the atomic number really to find a lot of times in these nuclear equations, sort of the missing element, if you will. And again, you could use it to figure that out. And then you can obviously add up the mass numbers to figure out what the missing mass number is. Remember, as we talked about, most of the time, probably when you do that, the missing atomic number will be an element, but it could potentially be a particle, something like a neutron or something like that, that may be missing. So just keep that in mind. But probably most of the time, if you go to the periodic table, it will be some type of element. All right, so a couple other things about that as well, some common terminology. If something is emitted or decays through some type of emission, usually that means is that particle will find its way to the product side of the arrow. And if you have something that is bombarded, or most commonly an electron capture, so those type of things would be found on the reactant side. So if you bombard something with a neutron, you would find that on the reactant side. If the reaction was an electron capture, you would also find that electron on the reactant side. So those are some common terminologies that sometimes you come across when you're doing that. Any questions on stuff we sort of talked about last time before we kind of continue on? And again, a reminder that if you do have questions, feel free to ask them and we'll get those answered. All right, so again, we sort of touched upon this a couple of times last time and just a second ago as well, but just to remind you, there's a very big difference in terms of sort of chemical processes and nuclear reactions or processes that occur. So as we've talked about, what usually happens in a traditional chemical reaction is we really are only kind of changing the electrons. Those guys on the outside of the atom, they're flying around. Either they're going to be gained or lost, they're going to be shared, but there's really no change that occurs to the nucleus in those atoms. And that's really important because, again, in the nucleus, you have your protons and you have your neutrons. So if you have no change occurring to the protons or neutrons in an atom, in a chemical reaction, that is why we do see that conservation of elements as you go from reactants to products. So again, if you started with 4 carbons on the reactant side, you should end up with 4 carbons on the product side. Again, the only difference may be that those 4 carbons may be in a different species on the product side than where they started on the reactant side. Now, that is very, very different than what occurs in a nuclear reaction. In a nuclear reaction here, we do change the actual kind of components, if you will, of a nucleus. And since the components of a nucleus are your protons and your neutrons, as those protons change, as we just talked about, everybody has its own unique atomic number. So as you change the protons and they get converted into other particles, you are changing the elements, and we no longer have that sort of conservation of elements like we do in a chemical reaction. And as you can imagine, since that is the nucleus, that's sort of the heart of an atom, there's a lot of energy sort of change that occurs as you start transforming those particles from one particle to another. So usually in comparison, as we will see as well, in a chemical reaction versus a nuclear reaction, there's a tremendous difference in terms of the energy sort of output, if you will, in those reactions. And again, because in one, you're really just changing electrons, not really transforming an element into something new. In a nuclear reaction, you are really kind of transforming an element into a new element. And obviously, that's a tremendous amount of energy required to do those sort of processes. So let's take a look again at some of these reactions that are occurring and sort of what's happening. Some of these we sort of talked about, but I'll just rearrange a couple of things here. There you go. I could actually see the screen, so that's good. All right, so we have our beta decay. So again, in each of these processes over here, beta decay means basically you're going to emit a beta particle. For our purposes, you don't have to worry about these guys here. These guys here are just sort of an indication that, you know, some of the mass will be converted into energy, so we won't worry too much about that symbol or anything like that. But what's essentially happening, again, when we go through a beta decay is we're decreasing the number of neutrons by 1, and we're increasing the number of protons by 1. And that's why, although you look at sort of the overall reaction here, that is why we are not basically changing the mass number, because in this process, what we're essentially doing is a neutron that's in the nucleus is being converted into a proton, and as a result, a beta particle is being given off. So if you think about how come perhaps the mass number doesn't change in this case, and that is because when we lose that neutron, our mass number would go from 14 for the first guy there, for example, down to 13. But we then just gained a proton, which means the mass number would then go back up to 14, yeah? And that's why overall, when you look at it, it doesn't look like the mass number has changed, but we basically replace that neutron with a proton. And that works out to the same mass number because, again, the mass number is our number of protons plus our number of neutrons. So again, although in this process we're losing one of these, we're gaining a proton, which basically cancels out any change that basically occurs to our mass number. And that's why, again, you see basically the mass number will stay the same. But we do see, again, an increase in the bottom number, which is our atomic number, and that is from the result of gaining that proton. In a positron decay, we're basically increasing the neutrons by 1 and decreasing the protons by 1. You would not. So the question is, I guess, just by how looking at it, the equation, would you know if a proton was increased or a neutron was decreased? So in general, when you see from the actual equation, because obviously in most cases, perhaps you would just have this part of it sort of provided to you, if you will. And since you just have that part provided to you, sort of the idea of what happens when a beta particle is emitted or how we get a beta particle emitted is this process over here. So this process here is essentially what's happening to emit that beta particle. And that process just automatically means that a neutron is going to really be converted into a proton and thus releasing a beta particle. So by seeing the beta particle, technically speaking, you would know that a neutron was converted into a proton. In terms of balancing a nuclear reaction or anything like that, you don't have to worry about, that in terms of figuring out the mass number or atomic number. If, again, this guy was not provided and you're trying to figure it out, it would all work out the same for you in terms of the mass number and atomic number, because you have 14 on the left, 0 on the right, which would give you 14 as your missing mass number. And you have 6 on the left and minus 1 on the right, which means you need to increase the atomic number by 1. And that's another way that you would be able to figure out that you at least increase the proton, is because the beta particle itself has that minus 1, which means you technically need to increase the atomic number by 1, right? And when you increase the atomic number by 1, you're increasing the number of protons, right? Because that's the atomic number. So a couple of ways you could sort of technically figure out sort of what's happening is the understanding that a beta particle results from a neutron being converted into a proton, and that's how you sort of release that beta particle. Or again, you could look at the atomic numbers on the bottom there and see you need to go 1 more in terms of the atomic number, and that means that you had to increase the number of protons by 1. Other questions on that? So a similar sort of thing here with our positron decay, we're going to actually increase the neutrons by 1 and decrease the number of protons by 1. And again, what's happening here overall to produce this positron is we're converting really a proton into a neutron. And the process of doing that will release what is known as a positron particle. And here again, if you sort of want to, like the earlier question, figure out sort of what's happening, you can see that with the positron emission, in terms of the atomic number, you actually need to go 1 back, right? So you need to decrease by 1. And when you decrease by 1, that means obviously you are losing a proton, right? Because your atomic number is getting smaller. And obviously that is what we're seeing here. A proton is going away. And again, our mass number doesn't change because, again, in this process, as that proton is being converted into a neutron. And again, that's going to add into our neutron, our mass number total, and we're going to end up with the same mass number. So again, if you just want to think about step by step, your mass number of carbon there started at 11. When it loses the proton, it drops down to 10, but then it makes a neutron, so it goes back up to 11 and ends up at the same number. Now, electron capture again is the one where we would see the particle on the reactant side, and that's what we do see here. And in an electron capture, we're increasing the neutrons by 1 and decreasing the protons by 1. So basically what's happening here is our proton and our electron gonna come together basically and produce a neutron. And if you just do the math on the proton and the electron, 1 plus 0 on top gives you 1. 1 plus -1 on the bottom gets you 0. And a 1 and a 0 is a neutron that is being formed. So again, here, what we do see is we do see on the bottom, if you look at the top equation there with the argon, our atomic number went from 18, it then changed to 17 on the product side. That means, as you can see there, we decreased the number of protons by 1, while our mass number at 37 stayed to 37. But again, kind of the same process as we've been talking about. If you sort of want to follow it through the steps, which I'm not sure is exactly 100% correct, but you started at 37, you lost the proton, which would drop your mass number to 36, but then you gain the neutron, so it goes back to 37. So again, overall, you get really no change in the mass number. Technically speaking, you are converting a proton into a neutron. So there is technically a change that's occurring between the protons and the neutrons, although in the overall balanced equation, if you looked at the overall balanced equation, it may look like nothing is happening in terms of our protons and our neutrons, but there is actually a change that's happening. Again, in this case, we would be down, technically speaking, 1 proton and be up 1 neutron from where we started with. And again, although that sort of cancels each other out in terms of what's happening, there is actually some changes that are occurring to the protons and the neutrons. And again, this is our basis of our nuclear reactions. We're changing those subatomic particles in the nucleus. In an alpha decay means that an alpha particle will be given off, as we can see here. This is sort of your biggest change that occurs. We actually decrease the neutrons by 2 and decrease the protons by 2. And overall, we do see that the atomic number goes down and our mass number also goes down as well. Since we're decreasing both neutrons and protons by 2, that's a total of a 4 in terms of the change for the mass number, right? As the mass numbers are protons and neutrons. And that's where we see sort of our biggest change. Now, fission, there's a process of fission where you have sort of a nucleus that will basically go through decay by itself. It will split off into a couple of new nucleuses and some neutrons, as we see down here. And that's a reaction that we'll talk about as well. So here's a picture, and you have a table, not this exact table, but I think you have a similar table in your book that sort of shows you the changes that are occurring. All right. So why don't you try this one here? Take a minute or so. You want to write the nuclear equation for the positron emission of potassium-40. So again, see what you come up with, and we'll check in just a second. Okay, so let's take a look here. So remember, we're starting with potassium 40. And if you're not sure when it is written like that, the 40 does represent the mass number. So that means we would have our potassium 40. We could use the periodic table there to figure out the atomic number, which is 19. Positron emission, again, the key word here is emission. That means we're going to give off a positron particle, which again, you could either use as the beta symbol with the +1, or you could use, again, the E symbol if you like, with the +1 as well. And that means that our missing atomic number would be 19 minus 1, which would be 18. And if we go to periodic table there, number 18 is argon. For our missing mass number, again, although there is really stuff happening between the neutrons and protons, overall in terms of the mass number, 40 minus 0, we are going to end up there with our same mass number. And this would represent our balanced nuclear equation. Again, remember, a balanced nuclear equation means that the mass number on the left, when you add them all up, equals all the mass numbers on the right. And same thing with our atomic numbers on the left. When you add them all together, it equals the atomic numbers on the right. Any questions on that one? So again, here, as we were just seeing there previously, although we are doing a positron decay and our mass number is not changing, again, we are changing a proton into a neutron. And that is why overall what we see in terms of the mass number, it stays the same. Any questions on that particular one there? Okay, you got a few more to go here just to make sure. So take a few moments here and write the balanced nuclear equations for each of these, and take a few minutes, and then we will go over each of them. Obviously, a periodic table would be super helpful. You're chemistry students, you should have one hopefully somewhere, I hope. So use those and see what you come up with, and then obviously we will talk about it. Okay, let us take a look here and see how we're doing. All right, so like I said, when you're balancing these nuclear equations, overall, it's not tremendously difficult. Obviously, very helpful is having a periodic table. So I probably should grab one here. Let me see. Got it. Okay. So again, uranium 238. That 238 is going to be the mass number. So that'll be a 238. We can find the atomic number from the periodic table, which looks like a 92. A alpha emission, so emission is going to be on our product side. And again, for the alpha, you could use either the helium symbol if you like. You could use that alpha symbol if you like. They're both perfectly fine. And again, we want to probably here start with the missing atomic number. So we have 92 on the left and 2 on the right. That gives us 90 when we subtract that. And number 90 there is TH on the periodic table. And 238 minus 4 for our mass number. That's a lot of math there, but I'm going to go with 234 there on top. And that again should give us our balanced nuclear equation, balanced mass number, and balanced atomic number on each side. Neon 24, again, going to be our mass number up on top. From the periodic table, we see number 10 is neon. Emission, again, going to be on our product side. You could use the E symbol with the -1. You could use the beta symbol as well. Again, either one's perfectly fine. So if you want to use that beta symbol, that's okay as well. Again, with our beta particle, because it is negative, we're going to have to actually go up in terms of atomic number. So we're going to have to go to 11, as 11 and -1 is 10. And that's going to get us to sodium. And our mass number here, as we were talking about, although there is stuff occurring, the overall mass number will remain the same. Coming down to our next one, which is nitrogen with a mass number of 13. 7 is its atomic number. Here, a positron emission going to be given off there. And here I'll use the beta symbol. But again, you could also use the E as well with the +1. So that means our atomic number on the bottom is actually going to go 1 less. So we're going to go to 6. And 6 is carbon. And up on top there, again, although it doesn't change sort of numerically, there is stuff happening, but it still remains at 13. And lastly here, we have our beryllium with its mass number of 7. From the periodic table, we see something. There it is, 4. And again, here an electron capture. So this is a little bit different. Electron capture means we are going to capture an electron. And that's going to give us 4 plus -1 on the bottom, gives us a new atomic number of 3, which is lithium, and 7 up on top there. So remember, there's really probably 2 things that you'll see in these things in terms of being on the reactant side: electron capture and something that's bombarded. So the V sort of stands for, and again, for our purposes, like I said, you don't have to worry too much about it. It does stand for a neutrino. We're not going to really sort of deal too much with that, so you don't have to include those in any of your reactions. That's exactly what it actually stands for. Yeah, so for our purposes in here, well, you don't have to include any of those. It's just sort of like, again, a little bit of mass that converted into some energy and stuff like that. It actually is a neutrino, but you don't have to actually include it. So you could just write the reactions like this. Other questions on these? Let's see, for the beta emission for the neon. Yeah, so again, you can use either symbol. They're sort of commonly used. So for a beta particle, it's okay to use this or this. For a positron, they actually use sort of the same symbols. You got this, or you could use this, but it is the +1. And even an alpha particle has kind of two symbols that are commonly used, which are these two. Yeah. So a lot of these guys do have sort of two different symbols. It's okay to use either one for our purposes. But typically you do want to obviously include in these things both the mass number and the atomic number when you're writing them. And like I said, definitely though, if in a book problem or something like that, you may see people just use the beta symbol, but sometimes they will also distinguish it. If they don't put anything there, it's probably safe to assume that it is the beta particle. Uh, Sometimes they will use that and put like the plus up on top there, which would indicate that it is a positron and stuff like that. So definitely, if it is the positron one, since they sort of obviously use the same sort of symbols, they usually will have that plus in there somewhere. So they'll usually do that. Okay. All right. Other questions on that? Oops. Okay. All right. So that's balancing nuclear equations. Again, not too difficult. Again, periodic table probably super helpful when you're doing it. And again, looking at that atomic number first allows you to figure out sort of what's missing. So what we're going to talk about now is a couple of things about stability and sort of how to determine stability, or things to look at when we determine stability. And one very common way that we look at stability is we look at what is sometimes referred to as the N to Z ratio, N being the number of neutrons, Z being the protons or the atomic numbers. And if this ratio is too high or too low, it will result in the nucleus going through some type of decay. So let's talk about the types of decays that these guys will undergo if the ratio is not so good. So for example, if you do the neutron to proton ratio, the N to Z ratio, and you find it's too high, and in just a second we'll talk about sort of what's high and low and what's an acceptable one. What will happen is neutrons will be converted to protons, and it will go through a beta decay process. So that particular element will go through a beta decay. And what that will essentially do is, if it's too high, kind of above the curve, if you will, by going through that beta decay process, is going to move it closer to a more acceptable level in terms of stability. It may not perfectly move it 100% to a nice stable sort of ratio, but it will basically move that particular guy into a more stable situation. Again, one sort of decay process may not move it perfectly stable, but again, it should be moving in that stable direction. If the N to Z ratio is too low, protons are converted into neutrons, and this happens via two separate sort of pathways. It could happen. One is a positron emission, and one is an electron capture. So you could also do an alpha decay. Is not as efficient. So for things that are too low, we will stick with a positron emission or electron capture. So you may say to yourself, you could do both, and you can. So just as an example, I think we could use the last one we just did there. So if we did beryllium 7 there with our electron capture, just like we just did. So if we take our beryllium 7 that we just did there in that last one, and we did the electron capture, which again is this, and that's going to give us our lithium over here. And this would be an electron capture. But if we were dealing with our same guy here and he decided to do a positron emission, a positron emission would look something like this. And that would be our missing guy would be 3, 7, and lithium. So you can see that regardless of which way that you go there, an electron capture or a positron emission, you are going to end up with the same element at the end. So when our ratio is too low, you actually have sort of a choice. You could do either one. They both in the end result will get you to the same basic element at the end. So those are two things to remember. Too high, beta. Too low, going to do one of those two things there as well. So how do we know if it's stable or not stable, what a good ratio is, if you will? And this brings up this little curve over here. And this little curve is what is sometimes referred to as the valley of stability, or some books and some people call it the belt of stability. And that belt of stability is sort of that yellowish area that we see here. And that is really where we get a lot of neutral, not neutral, I guess, more stable elements. It's a better way of wording that. And it is sort of broken up by atomic number, which is Z. So for guys that have an atomic number of 1 to 20, a stable ratio is 1. When you go from about 20 to 40, the stable ratio is 1.25. 40 to 80, the stable ratio is 1.5. And then pretty much anybody above like 84 there, 83, 84, there's really no stable guys. So you're not going to have a good ratio. So when we talk about being too high or being too low, too high would put you like on this end of this valley of stability. And again, by going through a beta decay, it's going to bring you down towards it. Again, in one sort of beta decay, for example, it may not perfectly put you right on it in terms of stability, but it should move your ratio closer to where it should be. And vice versa, if you're sort of on the low side, just for purposes, we'll draw a circle here. When you go through either your electron capture or positron emission, is going to kind of bring up your ratio and move you towards a more stable sort of situation. And again, it may not hit perfect. It may not be perfect in terms of that ratio after it goes through the first process, but it will move you closer to it. Now, in these type of questions, you're oftentimes asked, is this sort of nucleus, is it stable or not, this nuclei? And if it's not, then, what is the product of the decay that will happen? So usually when you're asked that, what you have to do is just one sort of decay process. You don't have to keep doing it until you get that perfect ratio of, neutrons to protons. You just have to do that one process. So these are the cutoffs, and a couple things about these cutoffs. And for us, just to make it a little bit easier, we're going to use these cutoffs as sort of hard cutoffs. And I guess what I mean by that is if you have somebody between 1 and 20, the ratio is 1, and either the ratio is 1 or it's too high or too low. And if you have somebody between 20 and 40, the ratio is 1.25, and either it is 1.25 or it's too high or too low. I will say that some people in some books, there's some grayish areas, if you will, as you transition. So for example, you could even see here going from 1 to 20, and then the next one is 20 to 40. So 20 is in both spots. And then 40, as you can see, is in both spots as well. So sometimes when you get sort of in that gray area where it sort of transitions from, say, 20 to 21 or 40 to 41, some people will say, well, it's not exactly 1, but it's still less than 1.25. So, it's still okay. So just to cut out any of those sort of like, is it in that grayish area or not? Just for our class and purpose-wise, we're going to do sort of hard cutoffs. So either it is that number, that ratio, and if it's not that ratio, it will be too high or too low. I will say again, in books and so forth, you may see some of those in those grayish areas where they still will say it's acceptable, because again, it sort of falls between the two sort of cutoffs. So I hope that sort of makes sense what I just said. Why don't we take a look at some here, I think. All right, so why don't you give it a go here? Predict the kind of radioactive decay magnesium-22 will undergo, and while you're at it, write the balanced equation. So take a moment or two and think about it and figure it out. Okay, let's take a look here. So we could just start with magnesium. The 22, again, going to be our mass number. We go to the periodic table and see that our atomic number would be 12. So we're looking for the N to Z ratio. So number of neutrons, again, is mass number minus atomic number. That looks like a 10. And that's going to give us 10 divided by 12. And if we do that, looks like we get 0.833. And remember that this is a 1 to 20 situation in terms of the atomic number, which means the acceptable ratio should be 1, right? Which put us here. And that means that our ratio is too low. And when it is too low, it has really two options. It can do a positron emission or an electron capture, right? So if we did our magnesium with a positron emission, that's going to give us an 11 and a 22, which would be sodium. Again, you could have done the electron capture as well. And the electron capture equation would look something like this. Remember, electron capture means we are electroning there. And that's going to give us an 11 and a 22 up on top as well. So again, you'll get the same emission product, regardless of which one that you sort of choose. Now we could actually look at what we produced and see if we are moving in the right direction. If we look at the sodium here, we have 22 minus 11, which is 11 for the neutrons. And that means that our N to Z ratio in this case would be 11 divided by 11, which equals 1. Yeah, so we definitely moved into a better, more stable ratio by going through one of these processes. Now, as I was saying earlier, it may not always happen that way, that like it did in this particular example, that we hit the perfect ratio after that sort of process, but it definitely should move you towards that correct ratio. Any questions on that? All right, I think got another one here, I think. So why don't you give this one a go here and see what you come up with. The N to Z ratio, N is neutrons. So neutrons is the mass number minus the atomic number. And Z is the symbol for the atomic number, which is basically the number of protons, which is what you find on the periodic table. So that's why on the last one we took the, it was 22, I think, for the mass number and 11 there for the atomic number. So that gave us 11 for neutrons. All right, so take a moment here and see what you come up with here for our krypton 85. All right, let's take a look here. So we got krypton 85. So again, our krypton with our 85, which is our mass number, which is our neutrons and our protons. From the periodic table, we see krypton is 36. That means the number of neutrons is going to be 85 mass number minus 36, which is our atomic number. And that gives you 49. And that means our N to Z ratio in this case is going to be 49, which is our neutrons, divided by 36, which is our protons. That's going to give us a N to Z ratio of 1.36. So we want to look here again at that sort of chart that we had, and we're between 40, which I guess it was there. But our acceptable ratio with a atomic number that's between 40 is 1.25, as we can see. And that would put us in this range. So an acceptable stable ratio was 1.25. So in comparison here, we are too high. And when we are too high, this guy will go through a beta decay. And that means that we would have 8536. Beta decay means that the beta particle will be on our product side there. We need to go one up in terms of the atomic number. So we're going to have to go to 37. 37 is going to be B. And our mass number will be 85. So this would be our product that was made here. And this would be the balanced equation for that decay process that's occurring. Any questions on that? Now here, if we look at the ratio of what we formed, Our neutrons would be 85 minus 37. That's 48. Our protons would be 37 in this case. So if we divide that, we're down to like 1.3. And you can see it's not perfect at that point, but it is definitely going in the right direction. We are definitely moving closer to that 1.25 ratio, and it'll obviously be more stable. So this was also what I was speaking about earlier. You don't need to kind of continue this process until you hit a perfect ratio. In these type of questions, you pretty much can just do what we just did here on the screen and stop at that point. So some people think they have to kind of keep going until they hit a perfect sort of ratio. Question on how to use the neutron to proton ratio for stability. Okay. So that's one common way to look at stability. There's also a couple other things that sometimes people will look at in terms of stability. And let's take a look at some other sort of factors that are sometimes considered in terms of whether or not a nuclei is stable or not. Obviously, the N to Z ratio that we just saw, the actual numbers of protons and neutrons, obviously affect the stability. But just in general, sometimes people will just look at sort of whether or not you have even or odd numbers of protons and neutrons. And for the most part, the most stability is seen when we have nuclides that have an even number of protons and also an even number of neutrons, as you can see on the table on the bottom. And again, this is not from your book, but you do have a very similar table, almost identical, I think, in your book. You have about 157 stable nuclides that have a combination where the protons and the neutrons are both neutral numbers, are both even numbers. Now, your next sort of best situation in terms of stability is an even number for protons, an odd number for neutrons. There you have about 53 that are most stable. Your third best, or your second worst, however you want to look at it, is an odd number of protons and an even number of neutrons. And lastly, sort of your worst situation you could get in terms of stability is when you hit odd on both of those. So you got like odd protons, you got odd neutrons. That is sort of the worst in terms of stability. In terms of nuclides, you can see there's only about 5 stable guys in that sort of arrangement. So positive and positive, or I guess not positive, sorry, even and even is sort of the best sort of situation you could sort of have. Now, if the total number of nucleons add up to a magic number, the nucleus is more stable. And it's sort of the idea like an electron configuration, everybody tries to get to sort of a noble gas configuration. There's a lot of stable sort of situations that occur when certain numbers are sort of reached, and most stable when either the neutrons or the protons are either 2, 8, 20, 28, 50, 82, and your mega number there is 126 for neutrons. So those are some of those sort of stable guys. Again, almost like a noble gas configuration. Probably the best way to do it, again, would be if you do have, obviously, the actual numbers of the protons and neutrons to calculate the actual ratio. That's probably a very good way to figure out stability. Again, probably second to that, if you kind of want to quickly figure out stability, you could use sort of what's in the table there, even, odd, odd, even, odd, and odd, in terms of probably stable or not stable. Any questions on some different ways to calculate or figure out stability? All right, so let's talk about a decay series. So in a decay series, it is basically much like it kind of sounds. It is a series of decay reactions. Remember that what we start with in terms of our radioactive nuclei is the parent nuclei, and what it decays into is, again, sometimes referred to as the daughter nuclei. And basically in a decay series, you have a series of these decay reactions that occur sort of one right after the other. And it will continue basically to occur until basically it hits something that is stable. And when it does hit something that's stable, it'll be sort of the end of the decay process. And there's really a couple ways you could kind of figure out, what you're going to end up with. And one way is, if you're not maybe interested in every sort of step along the way, you can count up the number of alpha decays and beta decays. And for every alpha decay, you could subtract 4 from the mass number, and you could subtract 2 from the atomic number. And for every beta decay, you could add 1 to the atomic number. So for example, let's see where we can do this here. We'll take a look at this guy here. Let's just say we did uranium-238, and let's see, let me find something better right on. I'll do it right here over this before that comes on. So let's say we had uranium-238. And obviously from the periodic table, you can figure out 92. And let's just say we want to figure out what we get after we did an alpha, we'll go beta and beta sort of decay. I'll just make it up here. And we stopped at this point. We want to know, hey, what do we get after that process? So the first way that you could sort of do this decay series is really just like you do nuclear reactions. You could start with your 238 and 92 uranium. Is first going to go through an alpha decay, which means your next missing atomic number would be 90 and 234 up on top. Again, going to periodic table, we see number 90 is TH. That would take care of that decay process. The next thing that would happen is actually your product here would go through the next decay process, which is also an alpha decay. And that would get us a new atomic number of 88 and 230 for the top there. And 88 is, where are we at there? RA. And that would take care, obviously, of that second one. Then your product of that step, your daughter, would become kind of the parent. It would then go through a beta decay. And here we would actually go up to 89 and 230, 89 being AC. And lastly, our product here, 230, 89, would also go through a beta decay, which would take care of that. And again, we would go up to 90 and 230, and 90 being our TH. So a good way of doing sort of a decay series is you basically can just write each of the individual nuclear reactions or equations like we've done before, where your product then becomes your parent and goes through the next decay process and next decay process. Or again, you can, if you're really perhaps maybe not interested in everybody along the way, but you're just interested in what you get at the end, you could do sort of the math approach if you want, 238 and 92. So we have 2 alpha particles that are going through decay, which means for each alpha particle, we're going to subtract -4 from the mass number up on top. So we're going to take 8 off of the mass number up on top. And for each alpha particle, we're going to subtract 2 from the atomic number on the bottom, which means we would subtract 4 from the bottom number. So if we just did that part of it, we had 238 minus 8 on top minus 4 on the bottom gets us to 230 up on top, and we get to 88 on the bottom. Now we also had 2 beta decays, and for beta decays, we add 1 to the atomic number. So since there's 2 of them, we would then add 2 to the atomic number, which means we would add 2 here. And you can see nothing would change up here. And that would give us 230 and 90. And again, we could go to the periodic table and get there as well. So, you know, sometimes if you just want to kind of quickly figure out what you get at the end of this is a very short, obviously, decay series here I just made up for sort of decay processes, but some of them are lots and lots of steps together where you might not want to write out each individual reaction. And if you're only interested perhaps in the final product, you could kind of use that just kind of math approach where you subtract 4 from the mass number for alpha and subtract 2 from the atomic number for an alpha decay. And again, for our beta, you would subtract, you would add 1 to the atomic number. Any question on that? Obviously, if you're asked what is the product of each step, it's probably just easier to write them out. So you could just calculate each one as you go along. But again, if you're sort of looking for just the end product there, you could kind of do it mathematically. All right. So here we can see again, this is a decay series for uranium-238. And it actually splits off in a couple of different sort of series or common series it ends. But it essentially will continue sort of this decay process all the way down here. You can see there's a lot of steps in these decay processes, which is why, again, you might want to figure out mathematically sort of what's happening at the end if that's all you're interested in, rather than doing each individual step. But it ends up somewhere at lead 206 in this case, which is sort of a stable process or a stable nuclide. So both of those routes, as you can see, is sort of diverges right around here. But in the end, they both really do end up in the same spot over here at the lead 206. So you do need to be able to, obviously, if to write a decay series, if you're given like, hey, you're starting with this and it went through alpha, alpha, beta, beta, whatever it may be, and figure out the products of each one in between and also at the end product as well. Again, it really is still just really nuclear equations to figure those guys out. Any questions on that there? Now, typically in a decay series, it will continue to decay until you basically do hit something that is stable. So unlike sort of those questions that we were just doing with the N to Z, where you pretty much could stop after the first sort of decay process, in a decay series, typically it will continue, obviously, until it hits something stable. So we're going to talk about kinetics, which is what we talked about way back when, at the very beginning. And kinetics of radioactive decay. All radioactive decay basically will follow, and try to write that better, decay, there we go, will follow first order kinetics. So if you remember first order kinetics, there's really a couple of important equations. And you can really still use the same equations that we talked about in kinetics. For first order, if you remember, it's basically the natural log of A equals the natural log of A naught minus KT, with our half-life equation being the natural log of 2 divided by K. And if you like, and I recommend it, why not? You can still use these equations here with nuclear chemistry. The only difference is in nuclear chemistry, they will sometimes use different symbols to represent kind of the same things. So a couple of different sort of symbols or words that we use in sort of kinetics, but it's really kind of the same thing, is in traditional kinetics and chemical kinetics, not involving sort of nuclear chemistry, the K is what is referred to as the rate constant. In nuclear chemistry, the K is sometimes referred to as the decay constant. And also, as we'll see, some people actually use lambda for that as well in terms of nuclear chemistry. Again, you can still use the little k just like we did in kinetics as well. T here is still the same thing. This is still time, not temperature. Now, also something different is instead of, say, concentration of A and concentrations, they will also sometimes use N. And they'll use N in place of A, if you will. And it just means nuclide. So we talk about sort of these nucleuses sort of decaying and so forth, and they're referred to as nuclides, and that's what the N will sort of basically stand for. But it's basically the same thing. I will say different than what we kind of saw in kinetics involving sort of chemical kinetics, not nuclear kinetics, is in sort of the regular kinetics that we did earlier. When we use this equation, we did use things like concentration, molarity, right, is typically what we used on both sides. And in kinetics involving sort of nuclear reactions, we oftentimes don't use molarity. We could use actually any unit you want. Technically speaking, you could put into this equation. A lot of times in nuclear chemistry, you may use grams and grams. You may use milligrams and milligrams. You may even use a rate of nuclear decay on both sides, like counts per minute, CPMs, you know, disintegrations per minute, something like that. So that's also slightly different. It works the same way. It just, in this case, it doesn't have to be molarity on both sides. You can use something like that. And again, they will use N as well. And you can see as well, very, very common. We do use the rates as a unit of in these sort of kinetics equations. The half-life equation is the same. Remember, the natural log of 2 is the 0.693 number, and again, it's divided by K. I would say oftentimes as well in sort of nuclear chemistry here in kinetics, you definitely a lot of times need to use both of these equations together. And a lot of times, because they'll oftentimes talk about half-lives a lot in nuclear chemistry. Obviously, the half-life, right, is the time it takes for half of whatever you started with to disappear. And they use it a lot in here. So a lot of times, again, you'll have to use that half-life equation to figure out the decay constant. And then you can use the integrated rate law to figure out, you know, how much is left over or how much time or something like that. So we also, again, see our familiar graphs for our first order. This is our natural log of our N over our time, giving us that where the slope here is equal to minus K. Here you can see in this particular book where I borrowed it from, they use this to indicate the decay constant, the lambda. And again, it is the same as K. Yeah, so it's the same thing as K. And again, here you can also see they use the N value. We also see the graph that we saw with first order as well, where you do just sort of the concentration versus time. You get that decrease with time, not that linear relationship that we see with the graph over here. And it's the same relationship, the natural log of N equals minus that plus this. Oops. And that is your y is equal to mx plus b. Again, on the y, natural log. On the x is our time. And again, you can see the slope here equals minus the decay constant, r again minus k. Whichever symbol you like to use is your choice. I'm perfectly fine if you want to use the same symbols, and the A's and the K's that we use with regular kinetics is perfectly fine here. Now, again, the half-life is how long it takes for half of whatever you started with to disappear. So again, if you started with 10, After the first half-life, you'll be down to 5. After the second half-life, you'll be down to 2.5. And after the third half-life, I should get a calculator to figure that out, but we'll move on from that. But some half-lives are very quick and some are very long. So you can see here, the couple up here, we have copper-14, which is 5,730 years. That is how long it takes for half of that to decay. It's a very long time. Uranium-238. Uranium, again, is used for nuclear reactions and like nuclear power plants. You can see the half-life of uranium is 4.5 times 10 to the 9 years. Unfortunately, none of us will be here after the first half-life, right? But you can still see things are very quick in terms of half-life. So radon-220 is 55.6 seconds. So essentially every minute, half of it is decaying away very quick. Usually after about 10 half-lives, it's pretty much gone, right? Because it's almost 100% of it. All right, so why don't you try this just to refresh your memory here on kinetics. If you have a 1.35 milligram sample of plutonium-236, how much will remain after 5 years? And here's some information for you, including the half-life of Pu-236. So take a few minutes here and calculate it. Again, pretty much approach it like a normal kinetics problem. See what you come up with. Okay, so let's take a look. So remember that pretty much all radioactive decay here will follow that first order kinetics. So we already know sort of the equations that we should be using. And again, if you just want to kind of roll with the same ones that we saw in that first chapter that we did, you absolutely can. Um, and again, a couple of first order sort of equations. And in this particular case, we are starting with 1.35 milligrams. So that's really our initial. And we want to know how much will remain. So that's really sort of our final, right? We want to figure out. After 5 years, so we do have the time. So really the one thing that we are missing here in order to figure out our answer is K, which again, the decay constant, if you want to sort of properly announce it there, or again, your rate constant, however you want to think about it. So again, we do need to use this equation here to really figure out our decay constant. And that's why, again, the half-life was provided for us. If for some reason it wasn't provided for you, you might have to go look it up in a table, like in a book problem or something like that. So K in this case would equal the natural log of 2 divided by the half-life. And that gives us the natural log of 2 divided by 2.86 years. And if we do that, gets us something like 0.242. The units here are 1 over years. And if you remember, the rate constant for our first order is 1 over seconds, 1 over some unit of time. And that's good as well. So we did get obviously the right sort of thing. Also, like we've talked about in regular kinetics, you do want to watch the units here between these two guys, the decay constant and the time, especially in sort of nuclear kinetics here. It may not always be the same unit. In this case, it happens to be the same. So we have years, right? And years. So everything's going to cancel out okay. So we can solve the natural log of A would equal our natural log of our initial. And again, as I mentioned, something slightly different here. We can just roll with it in its units of milligrams. We don't have to convert it to anything like molarity or anything like that. It's all okay. Minus the decay constant we just calculated times the years. And again, here, unit wise, we're good. Years and years will cancel. And technically speaking, this is milligrams, which means our answer should end up being milligrams as well. And if we clean up the right-hand side, we get the natural log of A equals, on the right-hand side, minus 0.9116911. Again, to get rid of the natural log on each side, we're going to E it, right? E. And that will give us our final concentration of 0.40, looks like 0.40. Again, here, milligrams would be our unit, as it was what our unit was at the beginning in this case. And a couple of things important to recognize, right? This is a decay process, right? Which means our final sort of concentration or amount should definitely be less than what we started with, which in this case it is, right? We started with 1.35 and we ended up with 0.4. So it definitely is coming downward from where we started from. We also see that the half-life was 2.86 and we went 5 years, right? So we did drop down, almost say 2 half-lives, right? Just a little under that. So we're just a little bit over 2 half-lives. So that's also good as well if you kind of roughly want to calculate, if you did 2 half-lives, you technically would be down to 0.337. And here we're a little above that because we didn't do 2 full half-lives, obviously, in this case. Any questions on that? All right, so really sort of radioactive decay, kinetics is pretty much all first order kinetics, just like we did in the very first chapter. So the calculations are pretty much identical. Again, the major difference is a lot of times for sure, you'll just use both of those equations together, the half-life and the integrated rate law. And I would say a couple of things that are different is you obviously probably won't be given molarity, but you'll be given something like this, milligrams. Again, you'll be given something like counts per minute or something like that, some type of rate of radioactive decay. And again, you just basically plug it in the exact same way. Any questions on that? All right, looking at the time, it's probably a good spot to stop here. So we're about half-ish or a little bit more, maybe the half through this chapter. So let's talk about what we got left, and what we got left is not a lot. Yeah, so we got one more week to go, and so hopefully we will knock out the rest of this chapter here on next Tuesday. And then after that, that basically will just leave us the organic chapter. So we'll hit some of the highlights, hopefully maybe Tuesday, maybe Thursday. We'll hit some of those highlights on that. And then that will be it in terms of lecturing. The final will be the following week. So we have, I think, a lab final on Tuesday, I want to say, a lecture final on Thursday, if I'm not mistaken. Now, in terms of next week as well, I believe on Tuesday is the start of the presentations, and maybe the start and the finish of the presentations. So a couple of reminders on that. Again, going off the top of my head, but I think the presentation is somewhere PowerPoint type presentation between 5 and 10 minutes max, I think, on your topic that you chose. We obviously will be doing it through Zoom here, just like we do our lectures. So you will have the ability to share your screen, and you're welcome, obviously, to share your PowerPoint presentation and do it through that. You will also have the ability, if you would like, you could open up your camera if you want to visually kind of display something. You could do that, which obviously, as long as it's appropriate, and your microphone as well, you could obviously open that and you could speak as well. I'll give you the ability during your presentation to share, and you could obviously, like I do with our presentations here, you could do the PowerPoint presentation. And again, it's up to you. If you want to do the camera component, you're more than welcome to do so. If you just want to do sort of the audio component, that would be probably the best here. So we're not just listening to nothing, I suppose. But if you want to do both, you're absolutely welcome to do that. We do start on Tuesday, and we're going to do it during lab. Okay. And I think in the next day or so up on Canvas, what I'm going to do is I'm going to put a sign up sheet. So you could kind of sign up maybe in order in terms of where you want to go or who wants to go first in terms of your groups and stuff like that. So keep an eye out for that in the next day or so. There might be an announcement on Canvas with a link to where you could kind of sign up on a list as to where you want to go in terms of groups and stuff like that. So we're not sitting on Tuesday going, all right, who wants to go? And everybody's muted themselves and quiet and all that good stuff, right? So we'll do it on Tuesday. Tuesday during lecture, we'll do our normal lecture. Then we will have the lab section where we will do those presentations. And my guess is we'll probably knock them all out on Tuesday, to be honest with you. And then on Thursday, obviously, we'll have lecture, and then we'll continue on if we need to on Thursday during lab time. Remember as well, your report is obviously due next week for that in addition, and there will be a spot on Canvas, obviously, for you to upload that. So you do need to just turn in one report if you're working, obviously, with somebody. If you're working with yourself, you still need to turn in one report, obviously. And, sort of the same rules apply for the report and everything, regardless if you're by yourself or you ended up still with a group of people in terms of those topics. Let's see. So I think that's it in terms of the presentations. Any questions on that? Okay, so let's see here. In terms of labs that are left, I think there's just the organic one, and I'm not sure we're going to actually do that lab or not. So we'll see where we are in terms of material and stuff like that. So that's probably all we got left on the horizon. So one more week, and then again, the following week, we have our lab final and our lecture final, which again, if I'm not mistaken, whatever it says on the syllabus, but I believe it's a Tuesday, Thursday combination, if I'm not mistaken. Any questions on anything on that coming up or anything happening? So let's see. We got that. Today is your last exam, right? So it will be available starting at 11:30. Again, same rules apply, obviously. Make sure that you answer all the questions online. If you do not answer a question online, your work for that question will not be looked at. If your answer online does not match your answer on your paper, it will not be looked at and you will not get credit either. Again, they do have to match. It's not like you submitted then decide how to do the problem later. So everything does need to match. It does need to be uploaded. I think 30 minutes, which is way more time than you should need. You should upload your work immediately, really, after you submit your exam. Again, if you happen to go outside of that window, which again should be way too much time anyways, you will not get credit for those problems. So make sure when you're done with the exam after you submit it, you efficiently, in terms of time, upload your work. There should also be a spot again and also a link where you can upload the textbook homework as well. So make sure that you do that and upload that as well. If you start the exam when you should, which should be at 11:30ish, you should not run into any time or problems. Again, if you start too late, the computer may cut you off and you will not get your whole time. So I highly recommend that you start exactly-ish, not exactly on the nose, but pretty darn close to 11:30 so you don't get cut off in terms of time or anything like that. Again, if you get cut off, you will not, the exam will not be open for you. Yeah, as I mentioned before, you could have some more time for chapter 19 since we didn't officially kind of finish it and stuff. If you have it done, you could submit it as well with this, or if not, what will probably happen is the assignment for the homework where you can submit it will, I think, just remain open. And at the point when you're done with your 19 and you want to upload it, you could upload it at that point. But technically speaking, really 16, 17 should definitely be uploaded today. Really, by this point, 19 you probably should have done as well. But if not, you could take a little bit more time for 19 and upload that. Other questions on that? Okay. So like I said, I think the exam should be pretty self-explanatory. There are some tables that are attached to the exam. So I put them there both as pictures, and just in case for some reason on your computer you can't see the pictures, there are PDF files for those tables that you could click and download and use, which is the same as what you see in the pictures. So just in case, I know sometimes maybe images don't work so well sometimes. If you can't see the image, then you should be able to click and download, the files to use and stuff like that. I think everything should be pretty self-explanatory. Do make sure that you do follow the instructions for each question in terms of how to input them, and make sure, again, for the most part, any numerical answer should not have any units or anything like that. Yeah, so just a reminder, technically speaking, like I said, you could hang on to chapter 19 a little bit longer if you haven't finished it, because we didn't finish chapter 19, I think, until last time. But you can submit it when you're done with it, as long as it's submitted before the end of next week, maybe. Yeah, this should be good before finals are over, I suppose. But the box for the homework will still be up there. So if you submit 17 and 16 and 17 today, you should be able to go back and submit 19 in the same spot. It'll still be open. Even if it's past the due date, it will still be open and let you submit it. So you could go back and submit it. All right. So like I said, everything else should be pretty self-explanatory. Other than that, have a good weekend after you're done taking your exam. If you have any questions, feel free to email me during the exam through Canvas. I do think, like I said, there hopefully shouldn't be too many questions. Do make sure you show all your work with the setup, the units, and everything if you do want all the points like normal. And then I will see you guys all again, I guess, on Tuesday. And again, keep an eye out for that sign-up sheet in terms of your groups and, kind of the order will sort of follow, okay? All right, good luck on your exam. Again, right now, I think the homework you should be able to turn in about 10 minutes or so. You should be able to start the exam and stuff like that. All right, good luck. Have a good weekend, and we'll see you next week for the final week of lectures.